OK, so in the previous video, we saw that, well, there's all these different ways in which I can write past the end of one buffer and start writing malicious things into the next variable. But it doesn't seem really plausible that someone's going to put a function pointer lying around in memory right after a buffer like name. Who would do something so silly like that? But it turns out something like that happens all the time, even if you don't realize it. And that's going to give us our first type of buffer overflow attack called stack smashing. So why did we just spend all that time talking about how functions get called and how functions return? Well, do you remember when we were talking about how when you call a function, you have to put some saved values on the stack? And when the function returns, we put those values back in the register? Well, one of the things that we put on the stack was the saved EIP. So that's a value that I put on the stack. And that value says, when I'm done, go to that address. Put this value back in EIP, go to that address, and start executing code. So if you really squint at it, that saved EIP that I put on the stack, sometimes people call it a return instruction pointer, or RIP, that value that I put on the stack, it's basically a function pointer. It's an address. And when I go to that address, I am going to execute the instructions at that address. So it turns out that example from before that seems so contrived, it's not so contrived. Everyone has code like that. When you write C code, you are putting function pointers on the stack, even if you don't know it. Because when you call a function, one of the things on the stack is, here's an address. When you're done, go there. And when the function returns, what do? You go there. You look at that address and go to that address. So we are going to exploit the fact that functions have a saved EIP on the stack. And we're going to change that value to cause the program to go to places it's not supposed to go. It's basically the function pointer attack from before, but on actual pieces of C code that you and I would write. So here is the picture of what the attack looks like. We'll set it up. So we have some function called vulnerable. And this time, I'm not going to put a contrived function pointer on the stack. I'm just going to say, here's a buffer called name. You might do that. Anyone would do this. I'll have a character array called name. And I'll ask the user, hey, what's your name? Give it to me. I'll use the getS function. And I'll write it into memory. What does the stack look like? Well, remember, when you call a function, you have to put the saved EIP on the stack. And you have to put the saved EBP on the stack. These are the two values that used to be in EIP and EBP. And when I'm done with this function, I'm going to take this value, stick it back in the EBP register. And crucially, I'm going to take this value, put it back in the EIP register. And another way of saying that is I'm going to take this value, which is an address. I'm going to go to that address so I can continue executing code from wherever I came from, whoever called vulnerable. So this code, when it executes, will create a stack frame that looks like this. It has these two saved register values. And the crucial one for us right now is this one, because that holds an address of where we're going to after the function returns. So then we call getS of name. What does that do? It says, all right, user, give me your input. And whatever the user gives to me, I will write here, and here, and here, and here. And if the user has a really long name, I'll keep writing and writing and writing. And I'll overwrite other things on the stack, possibly including this RIP address. And that's dangerous. So how would this work? So I'm going to give you a chance to try and put it together. So let's say the attacker has malicious instructions living at the address deadbeef, DEADBEEF. So what this means is if you go to this address and start executing instructions there, something bad will happen. You're the attacker. You want the bad thing to happen. So question for you is, if you want this bad thing to happen, like you want to go to this address and start executing bad instructions, what name should you supply to this code? So try and think about what characters will you provide to this getS call to cause those bad instructions to execute. So take a minute and think about it. If you're on the video, you can pause and I'll wait for you. If you're in person, take a couple seconds and ponder it. OK, does anyone have an input that they want to try? Anyone have a name that they want to try and enter? OK, give me a name. OK, so a random name that's 24 characters long, that's going to clobber out this box, this box, this box, this box, this box, and this box. That's 6 boxes, 4 bytes each, 24 characters. OK, good. And then I'll enter the address deadbeef right there. And then I'll add a new line. I'll hit enter to conclude my input. OK, that's great. That's exactly what I have too. So this is the input that we just talked about. We're going to enter 24 garbage bytes. Here I chose A, but you could have chosen Q or X or any letter you really liked. I'll enter 24 of those characters, clobbering out all of name and the SFP, which we don't really care about in this case, because I really care about changing this RIP address. And instead of having the address of whoever called vulnerable, main or someone, I'm going to change it to the address deadbeef, D-E-A-D-B-E-E-F. And then I'll hit enter. And then what happens now is, now when this function is ready to return, it's going to say, who called me? I'm vulnerable. Who called me? Like, who do I go back to after this function returns? I'm going to look at this RIP because this is the address of whoever called me. They put this address here. So when I'm done, I should go to this address. Well, it says deadbeef. All right, then. I guess I will go to the address deadbeef when I'm done. And when that happens, you are now executing instructions at deadbeef, and bad things happen. And one note here is, remember, we talked about endianness. When you have a 4-byte address, you have to start with the least significant byte. So we put the EF first, then the BE, then the AD, then the DE. Not a really important detail, but if you want this exploit to work, we have to follow the endianness rules of x86. So there it is. That's your very first memory safety exploit. Congratulations. We have exploited this program, and now it's going to execute instructions at deadbeef.